5 more seconds and we should be good. Okay, you got the notification?
Yep, you're live on YouTube. Okay, hey everyone, thanks for taking the time to join us. Today we have Shreya Shankar sharing with us about observability in production machine learning pipelines. So a bit about Shreya. She has industry experience. She was the first ML engineer at a startup previously, and now she's doing her research on observability. And she has a great paper that is also part of the optional pre-reading. Even if you haven't read it, I highly suggest you do that. But beyond that, also, I get the sense from Shreya's writing that she's been talking to a lot of people in industry. So she has quite a bit of good knowledge, I think, to share with us about this. So Shreya, please take it away.
Thanks, Eugene. Can you all hear me?
Yes.
Yes. Okay, perfect. Yeah, so I'm super excited to be here, especially excited because this paper just got accepted to VLDB 2023. So I'll be giving this presentation literally 13 months from now. It's probably outdated by then, but anyways, you guys get the first preview of it all. So I will be giving like a 30-minute talk or so on this. We'll try to get through what we can. Please interrupt if you have any questions. I don't know what the best way to ask questions is. Maybe post in the chat or post somewhere. Oh, I guess there's the link that Eugene posted. So I maybe we'll do questions at the end. How do people feel about that?
Yeah, I think maybe we can let you finish your talk and then we'll do questions at the end.
Perfect. Sounds good. Great, so let's get started. I'll be talking about observability for ML pipelines. This talk will mainly focus on the monitoring portion, at least research challenges in ML monitoring, especially as close to real time as we can get. But the paper has a whole hierarchy of challenges, proposed solutions for each, and I encourage you to check that out at the end if you haven't already. Cool. So I'll start with a little bit of a background on myself. I grew up in Texas. I went to elementary, middle school, and high school there, and then I moved out to the Bay Area for college. During college and a little bit after college, I did deep learning research at Google, specifically in adversarial examples. And that got me pretty interested in what's it like to train deploy ML systems in the real world. But the problem is I wasn't in the real world there. I was just thinking, well, how can we make models robust to quote unquote adversarial examples without thinking about what are the things that happen on a day-to-day basis when we deploy the models. So I went to applied ML startup to get experience with that. Turns out that it's not that there are people trying to craft inputs to fool your models. It's that data pipelines break and you have stale features, and that's why you get lousy quality predictions. So that helped me get a good sense of kind of the challenges in data management. Thought about starting a company, definitely did not. And now I am studying data management for ML at UC Berkeley. So my interests around machine learning have kind of evolved, actually not kind of, have seriously evolved. In my ML research days, I remember training lots and lots of models, but hardly doing inference with these models. And I said that I cared about robustness, but they weren't generating predictions that people used on a daily basis. I didn't have to deal with things that were outside like theoretical fairness or security. But when it comes down to production ML, right, we want to train our models. But every model that we deploy, we want to eke out all of the inferences possible from it before it goes stale or before it goes broken. And what does that look like? How do we get a good sense for when our models aren't doing well, and then quickly redeploy new models? And the big question that this motivates is what happens beyond the test set? If I evaluate a model in development, deploy it to production, how can I get a good sense for how well it will do? And then when it's doing poorly, how can I react in as real time as possible? So these are very hard questions, as many of you probably know. ML is kind of everywhere, and we're trying to use these models in our day-to-day lives, in products, etc. But it's really hard to get this kind of observability that I've been talking about. And I really love this quote from a blog post MLOps is hard because when you try to put a system in place around an ML model, the reality starts to set in. The whole point of MLOps is to kind of make the ML model lifecycle productionized, hardened, ready for the world without someone constantly babysitting. And maybe a lot of you are very familiar what it means to constantly babysit a pipeline like this, where you have multiple components in the end-to-end pipeline. You're taking some data in your data lake and transforming it through this insanely complex looking pipeline to get some predictions to serve to a client. And each stage or each component of the way you can choose from like 200 different tools. So it feels like a lot, at least it felt like a lot for me when I was doing this on a day-to-day basis. And I'm sure it's only become even worse, at least from when I talk to people. And it also makes the problem hard because all of these like different various configurations of the tech stack make it hard to get some bolt-on, I'll use the term bolt-on here, but like if I want to tack on observability, what does that mean? The definition that I use here is having better visibility into pipelines using data collected at runtime. In the paper, we talk about a three-pronged approach, which is also being piloted at a company that I'm collaborating with. But in these kind of verticals, we talk about detection. So how can you detect when ML pipelines or models in the pipeline are underperforming? Diagnosis, which is once you know or have an idea that they might be underperforming, why, like what component in the pipeline might be broken. Think of it as like taking snapshots of your pipeline and trying to trace back where the bug could lie. And then finally, reaction, which is we have an idea of where the bug might lie, but how do we best respond to the failure? Do we retrain a model? Do we collect new data? There are so many different ways that we could bring performance up, and like what's the biggest bang for my buck strategy to get there. So today's talk is mainly going to be around like detecting performance drops via monitoring. An interesting research challenge there around label delays and feedback delays. So I don't think I need to motivate this for you all. I think people know that we need to monitor, but I have this slide anyways. So one big need for monitoring is that data, quote unquote, drifts over time. And this is a loose term, but drifts can kind of capture any kind of engineering bug. Or, I mean, just natural data drift over time. Yeah, so formally, what does that mean? It means your distribution of training data is not kind of the distribution of what you're seeing live right now. Lots of great resources, especially from Chip out there for what drift kind of means. And there are multiple ways of thinking about drift, right? One is just the kind of shape of your input distribution, your x's change. The other one is the actual concept you're trying to model, which is y given x is changing over time. And you can like Bayes rule out so many other drifts if you would like. But the point here is like, due to any of these types of shifts, right, model performance can drop over time. And one thing that I've been thinking about a lot is you can kind of retrain your model maybe on recent data to get rid of these performance drops. But if your data that you're retraining the model over, like if you're trying to retrain on a recent window of data, if that data itself is like broken or there was an engineering bug in the pipeline that, I don't know, caused a bunch of columns to be null valued, how good will the newly retrained model do, right? So there still is like a need to do some sort of validation, or data validation is a buzzword, but to do some sort of monitoring over the data to understand like, hey, how do we make sure our latest snapshots of this data are clean, can be used to train a model. And here is an example of a figure I think that we have in the paper, where we use the New York City taxi cab data set and kind of analyze how distributions shift, or distributions of features change over time. The easiest example to look at is during COVID. Suppose I trained a model on January 2020 data, and then I wanted to know like, hey, is April 2020 data similar to this distribution. Obviously it's not, but this histogram kind of shows it for us there. Excuse me. So that's kind of the theoretical approach to why we might need monitoring, and even practically, right? Like when you have engineering bugs, you still need to make sure that your data quality, or you have a good assessment of your data quality. And another, I think, fun case study was this KDD paper that came out a few years back, where they tried to do early intervention systems for US police departments. And their motivation, well, okay, a model to predict whether we should intervene with some police officers. If the model is bad or the performance drops, like we need to know. And there are huge consequences that come out of this, like allocating interventions to the wrong officers or missing allocations to the high risk officers. So what did they actually do, right? The bottom line checks that they instrumented in their system were like data integrity checks, make sure our columns were complete, not missing data, etc. They had analysts comb through the data to kind of come up with custom data integrity checks, which, I mean, many of you are probably familiar with because this is what happens in organizations. And they did some form of anomaly detection, but they didn't talk too much about it. And then finally, they also monitored the model performance metrics directly, but they mentioned that this was really hard because the only way that they got ground truth data was from like police departments like sending CSVs of whether they correctly intervened with the officer or not. And I mean, if you're only getting that like once every quarter, once every half, like how you want your model performance metrics to somehow to be dynamically updating so you know when it's going bad. And so how did they do this? It was extremely customized. They talked about the difficulties of analysts like coming up with these data integrity checks and then leaving and then onboarding new analysts who had to, one, take the time to understand old data integrity checks, and then to build on top of those. So obviously, if people are coming and leaving the company, right, it becomes hard to keep maintaining these, especially when there's a lot of like really deep domain expertise. And it also, I don't know why some of my slides are duplicated, but it really motivates the question, right? Like, how do we take this, like the what column and abstract that away and do this in a setting that is kind of applicable across different data sets? Like, how do I come up with learned integrity checks, which is one of the papers I'm working on right now with Facebook, with Instagram. How do we do anomaly detection that's easy and scalable? How do we how do we proxy model performance metrics when you don't have labels? All of these things, right, are super interesting research problems to me, which really motivated the paper. And some practical things that make it hard to do this. One, like a pretty like distributed architecture of components in a pipeline. So your data might be in one place and then your compute cluster might be in another place. And then parts of your pipeline will be in like literally different countries, right? So how do you kind of, with different tools and different locations and everything, different services, how do you stitch them together? Because that's like the bare minimum to get some form of observability. And then two, which this is the problem that researchers love, feedback delays. And I have a diagram here that maybe looks complicated at first glance, but I'll explain it. But you can imagine like ML predictions being served in some sort of timeline from like t=1 to forever. And initially predictions are being made. And in some cases, as soon as a prediction is made, like you can get instantaneous feedback or near instantaneous feedback, like in recommender system. I shouldn't like broadly generalize this to recommender systems, but for some recommender systems, this happens. But in other cases, like especially in cases that I worked with before grad school, like I'll make some predictions. And in this case, like I have absolutely no idea how well my model is doing. I get some labels, ground truth labels for the predictions I've made, maybe like a week or two later, I get partial labels. So we call this like the partial feedback setting. And then like eventually we might get all the labels. Sometimes we don't even eventually get all the labels. But the point is, right, like how do we have good estimates for performance in each of these dotted lines? If I only consider like an inner join of predictions and labels, right, I'm missing out on assessing the quality of all the predictions that I have made that I don't have labels for. So yeah, how do we get better estimates? How do we know, or how do we estimate the accuracy for the predictions that we've made that don't quite have labels? This is a paper diagram. I don't think this is as necessary, so I'll move on to that. Okay, so thinking about kind of like monitoring, especially with feedback delays, what can we do? One thing that we could do is maybe monitor our input features only. And why is this suboptimal? I've kind of written about this extensively, and I'm also writing another paper on this right now. But there are so many distance metrics that you could monitor on features. And there's also so many different like statistics they could monitor, like completeness, number of frequently occurring values, and so forth on any column, right? You multiply that by the number of features that you might have in your data, and now you're all of a sudden you're monitoring like hundreds of thousands of things. You might have many features. You might have, if you're trying to run like 2 sample tests or like hypothesis tests, you might have too many data points for p-values to mean anything, something that we're seeing right now at Facebook. And like obviously like features are really tightly correlated for a lot of these models, and it doesn't make sense to monitor these independently. You can get like a lot of false positive alerts, leading to alert fatigue here. So I want to put another slide on this, because one thing that we're finding out at Facebook right now is you can do some sort of dimensionality reduction on your features and kind of monitor these clusters of features over time. And this works super well, reduces alert fatigue. But I guess stay tuned for that paper, which will be exciting. Yeah, so you can monitor input features only, not so great. You can hand label predictions on a cadence, which honestly is much better than not having any ground truth labels at all. But of course, it's still suboptimal because you make this choice of like which subsample of predictions to hand label. And another one of my like interview study papers, or one of my papers that's an interview study, which many of you may have been interviewed for. It's almost like which subsample of predictions is the easiest to hand label. And then those are the ones that get labeled. But if it's not like a true random sample of the live predictions that are being made, right, you might not get a good estimate. You might get a biased estimate of how well your model is doing. And then of course, right, you're tying another bad thing about this is you're tying your performance to this cadence, this arbitrary cadence that might not actually be all that frequent. So every week, every month, every year, like several people in the interview study mentioned, like they have a separate team of analysts that are sitting there and combing through live predictions and kind of trying to understand like how well the model is doing every day. Or there's like a separate BI dashboard that tries to approximate this. But a lot of ops work and a lot of like coordination goes into kind of like making sure that this cadence is slow or small, and it can be frequently updated. So this is also not ideal. Can we automate this ideally? And then the last solution is somebody gave this to me, and they work at a big company that I will not name. And they said, okay, I guess I named it. Yeah, so they said like, okay, we're only going to use machine learning for non-critical business problems because it's just too hard to monitor, and we don't want to lose too much money and lose too much sleep. And I guess this works if you're already generating like literally billions in revenue, but if your whole business is around ML, then maybe it's slightly harder to do. So again, not the ideal solution. Motivating more generalized frameworks. Cool. So finally, getting to kind of the meat of the paper. I mentioned this 3-pronged approach around detection, diagnosis, and reaction. I'll talk a little bit about detection now, and then we'll get to questions. But here, the objective, right, is to figure out or to approximate holistic ML metrics. For example, accuracy, with big challenges of missing and delayed labels. And I think there's also another interesting challenge of data mining the feedback delays. At a company that I worked at before starting the PhD, there were patterns to how labels were delayed, maybe depending on like Wi-Fi outages or networking problems. And this kind of helped engineers go and debug systems in those areas. And I mean, that's also another interesting problem. So getting into those, we are currently building out a logging and triggers framework in the vein of databases to maintain predictions and labels. And if you think about the ML metric as a view over the join of predictions and labels, and then you think about alerts as a predicate on this view, what values do we set, right? And how frequently do we materialize this view to get good estimates, metric estimates? And for unlabeled predictions, we dive into very, very old statistics literature using importance weighting to estimate the performance for unlabeled predictions. And I'll go into a very simple example of how that works. So on the New York City taxi cab data set, where we try to predict whether a passenger will give the driver some sort of tip, may or may not have been defined by undergrad. We use like off-the-shelf data management tooling, data frames, and sklearn model, which try to approximate accuracy. So the way that it works is you take your training set, you split it into buckets, and using some function, and you create the criteria for these buckets such that each bucket gets its own training accuracy. And then when it comes time to inference, you take the feature vector that the live vector of features, you figure out which bucket it corresponds to, and then aggregate the training accuracies for a set of predictions. So as a simple example, for this New York City data set, suppose I have a bucketing function that's basically the neighborhood of where I pick up a rider. And the buckets FIDI and Midtown, these are two neighborhoods in New York City. They have training accuracies of 80% and 50%, so super arbitrary. And maybe at inference time, we see 100 FIDI rides and 500 Midtown rides. Then a very crude estimate of accuracy we can imagine is 0.8 or 80% times 100 plus 50% times 500. And I really hope this math is correct. Otherwise, that would be really embarrassing. But you can imagine having like a strategy like this, but of course, like, what is this? What is the hard problem here? It's like, what is the bucketing strategy to have? And very simple bucketing strategies, very coarse-grained buckets, you might call it, might not quite capture like the variance in accuracies for different data points, but super fine-grained bucketing strategies. For example, like if I were to do a cross join between like distances and the pickup location ID, those might be really sparse, and we might have buckets that have no data points or very few data points, which will of course bias the estimate at inference time, right? So the research challenge here is, how do we design a good bucketing strategy? Like, what is the correct optimization objective? We're still working on this, to be able to kind of minimize variances within a bucket, but maximize them across buckets. And then of course, like adapt or incrementally fine tune the strategy, bucketing strategy, as new data points are observed at inference time. And this is still not ideal, because what if your P of Y given X is changing over time? Your bucketing strategy is only as good as your training accuracies, or it works for like subpopulate, or for I think it's called covariate shift. Yeah, covariate shift, just P of X changing. But it doesn't work very well whenever you have the concept shifting, or whenever so you do need some new labels in order to update the training bucket accuracies. Yeah. So I want to also make sure, okay, we still have a couple of minutes. Yeah, so unfortunately, like you still do, if you want to be robust to some sort of covariate shift, you do need at least some new labels coming in, which makes sense from like a common sense point of view. Like if my data changes so much, or the function I'm trying to model is like changing so much over time, at some point I need some new labels to get better approximations. And as you can see here, right, like during COVID, the actual concept is definitely drifting, and thus our kind of estimated accuracy diverges from real accuracy. But one thing also we're observing, at least one of the undergrads observed, is that you can still see the shape of the estimated curve decrease. Maybe it's not the magnitude of the real curve shift, but maybe it can tell us when models might be underperforming. Who knows? Okay, so I think actually it might be a good idea to stop here and answer questions, but I will leave it to the organizers what they think.
I think you said that you wanted to finish sharing about detection. Is that all for your slides for detection? If so, we can go into questions. If not, you can take more time.
We have a little bit more in detection, so let me.
Why don't we finish it? Yeah, we're flexible on that.
Okay, sounds good. Okay, so going into that, actually, this might actually go into diagnosis, but I still think that this is an interesting thing to do. Okay, so thinking about kind of drift even further, as I mentioned before, right, I think a lot of cases of drift, I wish there's like an empirical study on this, but a lot of cases of like drift, data drift, is just like there is an engineering problem somewhere in the pipeline, and like features are stale, or like the pipeline did not run, and so you get a bunch of null values. A lot of these problems are just like engineering problems that do need to be addressed and identified. Otherwise, you'll continue to have that problem unless you fix it. So suppose you want to understand kind of how your data is drifting over time. I think there was an interesting paper from Uber that came out that had like a proxy model to predict whether a data point. So essentially to like identify drift. Their argument was, if I can cleanly separate the training data from the inference data, then maybe the data has drifted somehow. And their idea was like, I'll train this proxy model as a binary classification problem to predict whether a tuple comes from the training data or the test data or the inference data. And then if this model cannot do better than random in identifying whether the tuple comes from whichever set, then I'm going to decide that these two data sets are indistinguishable and it's fine, the data has not drifted. And I got really excited by this because maybe I could have used it for my current job, but it's really hard to do when you think about incrementally maintaining this in production. So what they do is like fit a new model from scratch, very similar to like adversarial validation that you might have like heard about in Kaggle. They train a new model from scratch and they compute the AUROC, which is also pretty expensive. Every time that there's a new data point or like a batch of data points. And this, yeah, so like computing this metric is very expensive, and then fitting a new classifier every time you make a new batch of predictions is not scalable, at least in the settings that I'm working with. So how can we incrementally maintain this, right? And the insight here is that the users don't exactly care about the AUC. They want to know when their model is not performing. So they care about the shape of this curve changing. They care about the model not being able to distinguish between the two, or sorry, the model now being able to distinguish between training and live data. So how do we incrementally fit this? Exactly as you would imagine, we train a model. At every instance that we observe a new data point in the live data, we sample from either it or the training set with 50% probability. And then we incrementally fine-tune the proxy model. And as the loss of the classifier goes down, then we decide, hey, we can separate between these two and maybe there is drift. So you can see the diagram here, also in the paper. At the point where the AUC is going up, the loss also goes down. Cool. All right, I will stop there. then we can go to questions.
Fantastic. Well, I guess we have the Slido and we have a couple of questions in the chat, but I think could you go back to your previous slide, please? So you mentioned that the training data diverged from the live data by a lot. How would that happen? Isn't the training data based on log data?
Sorry, based on what?
Based on the logged data, and isn't the training so you would learn about your live data through logs, and your training data is also based on the logs. So in what cases would they diverge so much?
Imagine your training data here is like a snapshot. The actual data set that's being used to train the model, or train the user's model. Like this is a separate model that's being maintained. So that training data doesn't change, and at some point the live data kind of diverge from that.
So the training data is not updated increment. It's not a moving average.
It can be. So like, for example, a model I'm working with right now, right? Like we retrain multiple times a day, but if you think about it, still like for the model that's being served, there's like a fixed snapshot that it was trained on. Because we're not doing online learning. We are training like multiple times a day, but it's still not online. So you can still observe like a divergence.
Gotcha. Okay. So we have a couple of questions in the Slido, so I'm going to start with that first. First question, what's your view on unit tests? To verifying the implementation of data transformation or machine learning code can be brittle, especially if the assertions are done on data frames. What's your take on that?
Okay, so I think there's two types of tests, at least that I've observed from the interview study. One is like data quality checks, which you could also imagine are some form of unit tests. Like if I create a feature, I want to make sure that this feature function is outputting something useful every single time that I read from it. And then the other one is, I guess, I don't have a better phrase for it, but like model unit tests, which is my model can overfit to a small batch, for example, or my model like has the predictive power, or I've like designed the loss function appropriately to actually learn something. I think at least for the mature organizations that I've talked to, like they have both kinds of tests. I don't know what it means to verify the implementation of data transformation or ML code can be brittle.
So I guess maybe I would try to take a step at trying to understand this. For example, maybe we are writing some custom code to create features, right? And let's say we add a new column, and now your feature engineering custom code needs to consider a new column. Maybe you have expected output, and then all these changes. Testing on the data itself is very brittle.
Yes. Okay, so that's a great, amazing observation, and that gets back to the point where it's like the data tests. Coming up with data quality checks is insanely hard to do. There's like very low hanging fruit, which is like check assertions on the completeness of a column, like the fraction of nulls. And that is not going to change over time. But at the moment you start doing things like enumerating bounds, valid bounds for each feature, or anything that you can imagine is a function of that feature, then you need to constantly update this. As your data changes over time, you need to maintain this. And this is really hard to do, that we've seen in practice. So unfortunately, I don't think there's like a great off-the-box solution. There's a SIGMOD submission I'm working on that is like automated data quality metrics, kind of like, removing the need for users to enumerate these kinds of bounds and having them change over time. But right now, I don't think that there's anything super great. I think the basic things to do, like checking completeness, schema checks, those are much better than nothing and can flag like at least half, if not more, of problems. But like, there's still like a long tail of problems that are not addressed by current solutions.
Yeah, fully agree. I think, there's another question from Anonymous. It sounds like there's a very fine line between unexpected data drift and data corruption, as you present in your paper, and expected data drift due to seasonality, etc. How do you draw that line and false positives?
Great question. Okay, so if you had access to the real-time model performance and unexpected data drift, we've seen is like just a huge change or an unexpected change in the model performance. Whereas like seasonality or time varying drift, usually like the performance drops like pretty steadily over time. I mean, in both cases, they still drop, but like you can observe the patterns in the drop. And like one other interesting anecdote that I have, like one of the models that we're working on monitoring, it has like 25,000 features, if not more. And you'll notice certain kinds of like data drifts show up in different ways. Like, for example, there will be a lot of features that are only slightly corrupted. So maybe the coverage dropped only slightly, or maybe there will be a small handful of features that have like crazily changed a lot, like probably just because like the code is wrong or there's an engineering bug or something like that. So in that sense, like you can kind of reason through what's expected and unexpected. Like I think the way that I like to think about it is if the measure you're monitoring is like a function of the data, like you know how your ML model is also a function of data. So for example, if you're monitoring like the vocabulary distribution or something, that might drift over time unless you update those measures with respect to your data. Whereas like if you're monitoring something static, that's not like a function of the values in the data, like something like coverage, those can kind of help you detect like sudden shifts or unexpected drifts.
Makes sense. Well, I have a couple of questions from people. I'm gonna invite first, DB. I hope I'm pronouncing your name right, to unmute yourself. And maybe you want to ask your question in person. If not, I can also read out a question.
Okay, it's Devdeep. So I'm with Panasonic. So actually, right now we are trying several solutions for this. But I wanted to know there are some growing area of research in terms of this area of data drift. So what are your some of the favorite research directions, and especially from Percy Young's group and many other distinct groups? Yeah. So,
yeah, great question. I think Stanford in general is doing interesting research around like James Zhao's group, Chris Shreya's group. Both of them are like Mandolin, for example, came out of Chris Shreya's group, I believe. And they do some form of importance weighting. I think they do really interesting work. I haven't seen the distinction between like expected and unexpected data drifts yet, or like engineering corruptions versus like natural drift or shift, both which I think show up differently in the data and require kind of different approaches to fix. The other thing is I think like drift in tabular data settings is kind of different from drift in like NLP or like or different modalities of data, which is unfortunate. I think like drift, it's yeah, every time I've like talked to somebody about drift, it's always like a different problem depending on the task that they're trying to solve or the modality of data. So I don't, yeah, there's a lot of work to be done, I guess, in this area, but definitely a lot of cool ideas are coming from that lab.
Cool. Next, I'm going to invite Michael. He has a question on data modeling. Do you want to ask that question, Michael?
Hi, everyone. Yes, thank you very much for this presentation. So I was wondering, everyone is talking about monitoring in structured data. You can do Kolmogorov-Smirnov tests, you can do chi-square tests for categorical features. But when we work with raw texts, for example, or when we work with images, or even worse, videos, how can I detect the drift in images or in videos? Do I need to embed them somehow to load dimensionality space and then compute these statistics, or how? And it looks like there is no such tool in the world that allows you to monitor this. Maybe you know?
Yeah, I totally agree. Unfortunately, I don't do research in image and text data. I think Stanford papers will actually have more interesting information there. I've seen, so one of the things that we're doing right now is taking embeddings and just like running drift detection methods on embeddings, as you say. Clustering really helps before. So the problem with like running like a KS test, for example, on every single feature is then you get like some sort of alert fatigue, because the probability of at least one of these columns changing a lot, or one of these measures changing a lot, is pretty high. So if you cluster them, reduce dimensionality somehow, that really helps.
Yeah.
Sorry?
Yeah, you're right. You need to do at least like one Ferroni correction when you have a lot of KS tests. The probability that at least one feature will give you false alarm will be higher than
but even
0.05.
Yeah, but I think in my experience, even von Ferroni correction doesn't like. I guess it just changes the threshold for which you fire an alert, but it doesn't change the. It doesn't really make an effect, or sorry, make a change on like the probability that at least one alert fires, from my experience. So I still get a lot of alert fatigue in that case. But I think like really clustering and reducing dimensionality helps a lot. One thing we've noticed is even if you do have embeddings and you cluster them into just like a 10 to 12 groups, or cluster each position in the embeddings, and then you just average the p-values that come out of these, that works a lot better. The other thing I will say is Earth movers distance is a much better statistic for the kinds of drifts that we care about in the ML setting than the KS test. And maybe this is too technical, but the KS test is like the maximum difference between the CDF, and it is it's very possible for the maximal difference to be very high if only a small fractions of the records have been corrupted. But in ML settings, you want the performance drops only when like a sizable fraction of the records are corrupted. So for that sense, like Earth movers, like Wasserstein one is much better.
Wow, that's nice. What is the name of this? Earth movers?
Look up Earth movers distance. It's the same as like the Wasserstein one distance.
Okay.
Yeah.
Thanks a lot. That's very helpful. Okay.
Yeah, but I will say that SciPy doesn't give you p-values directly from that, so you will have to do some like population sampling, or like you'll have to bootstrap in order to get p-value.
Okay, nice.
All right, thank you for that great question, Michael. Next, I have Nanda Kumar. I'm gonna try to invite you to unmute yourself and ask your question.
Yeah, so my like nice presentation. So I wanted to ask, like, generally in MLOps, what are your opinions of using like a managed service, like a cloud provider for a service like AWS SageMaker, or like implementing something like using open source frameworks, using multiple open source frameworks? Yeah.
Okay, I feel like the other hosts of this are much better suited to answer this question than I am. But at least what we've observed in like organizations that we've talked to in the interview study paper is that people end up switching to a managed service just because it is easier to maintain, especially as the company scales. Like, for example, there's a lot of people I've talked to that are either using Vertex AI or switching to Vertex AI. Even though Vertex AI offers a billion things and maybe they only use 1% of what Vertex AI offers. We're just seeing that larger companies end up adopting these like managed solutions and using like 5% of each managed solution and stitching it together. So yeah, I guess that might not be the greatest solution, but it is the trend. So I'm curious though what other people have to say about more principled opinions.
Well, let me let people unmute themselves if they want to. If anyone wants to chime in, feel free to. If not, I'm going to move on to the next question. Okay, I guess we're moving on to the next question. Gustavo, do you want to ask your question? Okay, if not, I can ask on your behalf. Do you think that a good way to monitor your ML model is looking at your business and see if some money was lost or dropped?
Wait. Oh, I see. Good. Do you think good way more looking at your? Okay, I think this is a great way of monitoring your ML model if you can really directly map your predictions to a business metric like click-through rate, revenue, something. In practice, a lot of models can't be really directly mapped. The successful projects and successful pipelines are obviously ones that can be mapped, so they know how to respond when, or like they have like ground truth indicator for whenever the pipeline is underperforming. But like in the case where you have like intermediate embeddings from ML models, I think that's much harder to directly tie to business metrics. I'm sure others also have opinions here.
Yeah, I wanted to follow up on that. So in your industry chats, how have teams effectively monitored their business metrics, given that there are many variables that could affect it, right? Seasonality, traffic, etc. And how high or low level are their metrics? Is it as close to the customer as possible, like you mentioned, click-through rate, or is it like at the conversion rate or the revenue or units? What has been useful for them?
Gosh, I don't think I have a nice, succinct answer to this. Maybe I'll answer this in terms of like which pipelines get dropped or which pipelines like I guess the business doesn't focus on anymore and you could consider them like failed deployments. But these are pipelines in which the product managers, other stakeholders are not convinced of the ML pipeline's value because they cannot like directly see a change in whatever metric that they're caring about. So yeah, I don't think there's like a one metric, one business metric. I think like it's very like figure out what the product team or the business team cares about and is like monitoring on their dashboard, and then make sure your pipeline, your ML models bring that metric up somehow.
Gotcha. Thank you. So last question I have from Paul. Paul, would you like to ask your question?
Yeah, sure. Thank you. Great presentation here. Yeah, quick question here. So do you recommend any tools or frameworks for the first two steps of the monitoring, just like detection and diagnosis? I know we can come up with like a custom framework or something, but do you have any recommendation on these two steps at least?
I wish I did. The prototype that we're building, but this does require a lot of engineering work, so I don't know if I'd recommend it. Is we are like logging. I mentioned that like you can imagine like predictions and like labels or feedback as like different tables or different relations. But we're using like DuckDB to store all of this, and then we're using like some streaming service. Right now it's like timely data flow, but like it's probably something else to incrementally maintain the join between the two like window joins. I don't like. I wouldn't say like we are wedded to either DuckDB though or like timely data flow. So yeah, I'm sorry, I don't have a great answer to this question. I think others will.
Anyone want to chime in? Yep, I guess it's a difficult question. And last question we have. Oh, we have actually more questions on Slido. But I guess a question from Anonymous. In your industry surveys, how are teams organized and how do they share or split responsibilities across research, ML software engineering, DevOps, SRE, and Ops?
Oh, I haven't made this table yet, so I cannot give you numbers, but the table will exist after September 15th on archive.
Looking forward to that.
Yeah, so I guess.
I mean, are you able to talk at a high level ballpark?
Yeah, oh, sure. Yeah, at a high level, so we only interviewed ML engineers. I think some of them, or it's okay, the criteria that we interviewed like 20 people in like insane depth. But the criteria was that they had to have like deployed and like sustained a model in production for at least like several months or something. So maybe some of them were data scientists, but like they did a lot of this like engineering day-to-day works. So how do they split kind of responsibilities? Almost zero of them. I don't think any of them really did any research. Like if they had to work on like experiment ideas that would improve the performance, like they almost always like went to a data scientist, or they went to like a researcher or somebody like a data scientist who didn't like work on production models to get feature ideas and then try them out. So hopefully that answers the research question. The ML software engineering, I think honestly, I think they do a lot of both. Like they are sitting there progressively validating the model across multiple stages of deployment. So maybe that's ML, but also that's software engineering, standardizing evaluation across multiple teams. Also software engineering on like building feature stores or like monitoring services for other ML engineers to use. So I would say good split between like 50-50 split between ML and software engineering in that sense. DevOps/SRE. I don't think anyone that we talked to did like really traditional SRE. They almost always like talk to SREs at their company. Again, I think depends on what you mean by DevOps. Everybody was running like some form of CI, but yeah, the DevOps is so big. So hopefully that answers the question.
Thank you. And I guess we have another new question in the chat. Rohan, would you like to ask a question?
Sure. Hi, Shreya. I'm Rohan. I work at Headspace. I work there to build recommendation system. So one of the question I have regarding this recommendation system, that it is very natural for them to have like this data drift, and over the time user preference changes a lot. And so how we classify that, if we are monitoring such system, such changes like better or worse over the time? So where do we where can we draw such line that it should not drift, or it should drift over the time?
Okay. I think you might be asking like how to tease apart drifts that are not expected drifts, because you do expect them to change over time. Correct me if I'm wrong. Is that the question?
Yeah.
Okay, yeah. So I'll tell you what I have observed at the company I'm currently working with, as well as others. People doing Rexis frequently train their models like multiple times a day because data drifts. And when they're able to do that, then if performance drops a lot more than expected, then if the data is not changing, like the distribution is not really changing every like 10 minutes so much. So probably there was some engineering bug in the pipeline or like something unexpected that happened. I think, yeah, so the upside of this is like you can be somewhat robust to natural data drifts. The downside of this is you get like really terrible feedback loops if you had some sort of corruption in your data and then you retrain a model on that corrupt data, and then now you're like cycling through like terrible click-through rates or terrible recommendation performance. Yeah, so I guess that really motivates like having really good data validation or feature validation in your system. But yeah, I would say like starting with doing, or like having a researcher or like some data scientist at the company, like see what happens kind of if you train models super frequently or increase the retraining rate, then like deploy it to a small fraction of users.
Okay, I guess one last question from Melissa, and then we can stop the live stream. Melissa, would you like to ask your question?
Hi, Shreya. I just wanted to ask, like, where, since this is an emerging space for ML ops where everything is trying to race to be the best, and there's just a lot of proliferations of tool sets and and companies and, tools like Ray. I mean, I'm wondering what predictions are you think are forthcoming around what the ML stack in production will look like, or what do you hope it would look like?
Yeah, I think there's a really, really long tail of ML tasks and use cases out there, and there isn't going to be a one size fits all stack. It's probably not the answer that you wanted, but like the different orgs, different teams have different needs. It's going to be a function of like how frequently they want to update their models, how frequently their data changes. If you think of like every ML model as like just a view on the data that is operating on, then it's like the patterns in like the scale of the data and how the data changes will inform like their pipeline. So in that sense, yeah, there's a huge tail. I think it's very similar to like in the databases world, where it's like there's a huge tail of like DBMS or database use cases. And that's why we have a billion DBMSs out there. So yeah, I guess it's good news for everyone working on MLOps, because there is room for a lot of people.
Great, thank you.
All right, thanks, Shreya, and thanks everyone for the fantastic questions. We're gonna stop the live stream right now, and we're gonna invite folks, to come online. I mean, to share, turn on your camera, and then you can ask Shreya any other questions that you might have. So, thank you to everyone who's on the live stream, and I'm gonna open the floor to questions from people in the audience.